Welcome back. In the last lecture, we were doing the convolution or definition of convolution and the Fourier transform of convolution of two functions, as well as we have done the Parseval's identity for Fourier transform. Now, let us see the Parseval's identity for the Fourier cosine and sine transform also in the same way. So, the Parseval's identity for Fourier sine and cosine transform, the corresponding theorem is if Fourier sine transform of f x is capital F of S alpha and Fourier cosine transform of g x is capital G of C alpha, then 0 to infinity modulus of f x whole square dx, this equals 0 to infinity modulus of Fourier sine transform of alpha whole square d alpha, and similarly you can get 0 to infinity modulus of g x whole square dx is equals to 0 to infinity modulus of g c alpha whole square into d alpha. That means, if you see for the Fourier transform whatever was true, the same thing is true for the Fourier sine and cosine transform also, that is 0 to infinity modulus of f x whole square dx, this equals to 0 to infinity modulus of capital F s alpha whole square d alpha, that is modulus of Fourier sine transform of f x whole square d alpha, and 0 to infinity modulus of g x whole square dx equals 0 to infinity modulus of Fourier cosine transform of g x whole square d alpha. The proof I am not giving, because the proofs are similar as we have done for the case of Parseval's identity for Fourier transform. So, I am leaving it to you, you can do it of your own on the same fashion, it is identical. Now, let us see the applications. Using Parseval's theorem, I want to evaluate the integrals. The first integral is 0 to infinity x square by x square plus a square whole square dx, where a is greater than 0. The second one is 0 to infinity dx by x square plus a square whole square, where a is greater than 0. So, let us solve the first problem, that is 1, where we have to evaluate this thing x square by x square plus a square whole square dx. This is equals how much, where a is greater than 0. Now, from Parseval's identity we know this thing 0 to infinity modulus of f x whole square dx, this is equals 0 to infinity modulus of Fourier sine transform of alpha whole square into d alpha. This we know it from the earlier theorem, that 0 to infinity modulus of f x whole square dx equals 0 to infinity Fourier sine transform of alpha into whole square dx. Now, this you see the quantity x square by x square plus a square whole square. This is the Fourier transform or Fourier sine transform of which thing? If you remember this thing, Fourier sine transform of e power minus a x, this is equals root over 2 by pi alpha by alpha square plus a square. If you remember this thing, Fourier sine transform of e power minus a x, this is equals to root over 2 by pi alpha by alpha square plus a square. So, this we know it, and this thing matches with our given integral which we have to evaluate. So, once I know this thing, so using this property I can write down 0 to infinity modulus of e power minus a x whole square dx. This is equals to 2 by pi, this is nothing but 0 to infinity alpha square by alpha square plus a square whole square into d alpha. Just using this theorem, we can write down this thing directly, 0 to infinity modulus of f x whole square dx equals 0 to infinity modulus of Fourier sine transform of alpha whole square d alpha From there, since I know Fourier sine transform of e power minus a x is root over 2 by pi alpha by alpha square plus a square. So, I can write down 0 to infinity modulus of f x, that is f x is e power a x whole square dx. This is equals to 2 by pi 0 to infinity modulus of Fourier sine transform of alpha. So, modulus of this means 2 by pi alpha square plus a square whole square into d alpha. So, that you can write down 0 to infinity, this is nothing but e power minus twice a x dx. This is equals 2 by pi 0 to infinity alpha square by alpha square plus a square whole square into d alpha. So, once I am getting this thing, now this here the parameter is alpha. This parameter alpha I can replace by x, because I can make it any other parameter. So, I will obtain the integral 0 to infinity if I change the parameter alpha by x, 0 to infinity x square by x square plus a square whole square into dx, and exactly the value of this integral I have to evaluate. So, by changing the parameter on the right hand side from alpha to x, I can write down 0 to infinity x square by x square plus a square whole square dx. This is nothing but pi by 2 into the integral 0 to infinity e power minus twice a x into dx. And very easily I can find out the value of this integral. E power minus a x is already there. So, that pi by 2 into e power minus twice a x by minus 2a integration, where the limit of x will vary from 0 to infinity. And if I put the limiting value, I will obtain the result as pi by 4a. So, that the value of the given integral is pi by 4a. And please note one thing, that I am evaluating it how? Not directly, but using the Parseval's identity for Fourier sine transform, I am finding this thing. So, let us see this one. This was my problem. So, in the first case what I am doing, I know this theorem 0 to infinity modulus of f x whole square dx equals 0 to infinity modulus of f s alpha whole square into d alpha. Once I know it, from here I know this thing also. Now, you may ask me the question, suddenly from where you got this e power minus a x? You are just finding out the Fourier sine transform of e power minus a x. The reason is to me is that I know what is the Fourier sine transform of e power minus a x, which is of the form alpha by alpha square plus a square, and I have to evaluate the integral x square by x square plus a square whole square. That is, if I make whole square of the right hand side, then I will obtain my required integral. So, basically by observation I am finding out this, that this type of integral is appearing whenever I take the Fourier sine transform of e power minus a x. So, the observations I have to keep it in mind, and I have to remember what are the transform of which type of functions. So, now here what is happening, here your f x is this thing, here your f x will be this f x is e power minus a x, and your Fourier sine transform of alpha is nothing but root over 2 by pi alpha by alpha square plus a square. So, that if I use the theorem, this I can write down 0 to infinity modulus of e power minus a x whole square dx. This is equals 2 by pi 0 to infinity alpha square by alpha square plus a square whole square d alpha. I am making the whole square on both sides of this. So, that this I can write down 0 to infinity e power minus twice a x into dx, and this equals 2 by pi 0 to infinity this. Now, on the integral of the right hand side, the parameter alpha may be replaced by x, because any parameter I can use. So, that on the integral I can rewrite as 0 to infinity x square by x square plus a square whole square into dx, and this is equals pi by 2 will go on the other side. So, it becomes pi by 2 0 to infinity e power minus twice a x dx, and I can evaluate the integral easily e power minus twice a x by minus 2 a, where limit of x will be from 0 to infinity. If I substitute the limit, this value becomes pi by 4 a. So, that the value of the given integral is equals to pi by 4 a. Now, let us see the part 2. Part 2 of the given integral is, I have to find out this thing 0 to infinity dx by x square plus a square whole square, this value equals how much, where a is greater than 0. Again, if you see what is from here, any kind of function I am getting whose Fourier transform or Fourier sine transform or Fourier sine transform of this type. So, I am starting again Fourier cosine transform of e power minus a x. If you remember, it is nothing but root over 2 by pi a by alpha square plus a square. So, Fourier cosine transform of this thing is root over 2 by pi a by alpha square plus a square, and again I know it that 0 to infinity from the Parseval's identity mod of f x whole square dx, this is equals to 0 to infinity modulus of capital F of c of alpha, that is Fourier cosine transform of f x whole square into d alpha. So, if I use that property, I can write down 0 to infinity modulus of e power minus a x whole square dx. This is equals, whole square will come here. So, it will become 2 by pi 0 to infinity a square by a square plus alpha square whole square into d alpha. So, basically I have used this property 0 to infinity modulus of f x whole square dx. This is equals 0 to infinity modulus of Fourier cosine transform of alpha whole square into d alpha. I have used this particular property and I am writing this thing. Once I got this particular integral, this one, so very easily now I can write down the value of the given integral using the earlier method, that is, that line can be written as 0 to infinity e power minus twice a x dx. This will be equals to twice a square by pi, because a square was inside, I am bringing it outside, and it becomes d alpha by a square plus alpha square whole square. Again, this alpha parameter can be replaced by x, so that I can write it as 0 to infinity dx by x square plus a square whole square. This is equals to, then it becomes pi by 2 a square 0 to infinity e power minus twice a x dx, whose value I can find out very easily, pi by twice a square into e power minus twice a x by minus twice a x vary from 0 to infinity, and if I put the values, it will become pi by 4 a cube. So, the value of this integral 0 to infinity dx by x square plus a square whole square is nothing but pi by 4 a cube using the earlier property. So, just see it quickly. We are starting in the earlier case, we started with Fourier sine transform of e power minus x, because the form was alpha x by x square plus a square. Here the form is 1 by x square plus a square. So, we are considering Fourier cosine transform of e power minus a x, and this is nothing but root over 2 by pi a by a square plus alpha square. And once I am getting this, using the property, as I told, the Parseval's theorem, that 0 to infinity modulus of f x whole square dx equals 0 to infinity modulus of Fourier's cosine transform of alpha and Fourier cosine transform of f x whole square d alpha. If I use this property, then it becomes 0 to infinity e power minus a x whole square into dx. This is equals, making whole square on the both side, 2 by pi 0 to infinity a square by a square plus alpha square whole square into d alpha. Now, the right hand side integral I can write down, but before that 0 to infinity modulus of e power minus a x whole square, I can write down e power minus twice a x. Now, in the right hand side integral replace alpha by x, so that this I can obtain as 0 to infinity dx by x square plus s square whole square equals pi by twice a square into the integration will come 0 to infinity e power minus twice a x dx, which if I integrate I will obtain this, and if I substitute the value I will obtain for pi by 4 a cube. So, like this way, for evaluation of various integrals, value of the evaluation of various integrals means to find out the value of different integrals, I can use the properties of Fourier transform, I can use the convolution, I can use the Parseval's identity or theorem to find out the values of this. Now, let us see another theorem. This is an interesting theorem. You see, if capital F c of alpha and capital G c of alpha are Fourier cosine transform and capital F s alpha and capital G s alpha are the Fourier sine transform of f x, then 0 to infinity f x g x dx equals 0 to infinity Fourier cosine transform of alpha into Fourier cosine transform of f x into Fourier cosine transform of g x d alpha equals 0 to infinity Fourier sine transform of f x into Fourier sine transform of g x d alpha. That is 0 to infinity, whenever I am doing 0 to infinity f x g x dx equals, the values are equal 0 to infinity Fourier cosine transform, that is f c of alpha into g c of alpha d alpha equals 0 to infinity Fourier f capital F of s of alpha into g of s of alpha d alpha. Let us see the proof of this theorem. We will prove one by one. The proof is very simple actually. You can also think of, I am starting from the right hand side with this integral, that is 0 to infinity Fourier cosine transform of f x into the Fourier cosine transform of g x into d alpha. Just use the simple properties. So, 0 to infinity f of capital F of c of alpha means Fourier cosine transform of f x. Now, g c of alpha, this thing, that is Fourier cosine transform of g x, using the definition of Fourier cosine transform, I can write it as root over 2 by pi 0 to infinity g of x into cos of alpha x dx into d alpha, I can write down. Now, so basically what I am doing? I am replacing this g c of x, that is Fourier cosine transform of g x by the definition as root over 2 by pi 0 to infinity g x cos of alpha x dx. Now, without changing the properties, if I wish, I can interchange the order of the parameters x and alpha, that is I can integrate first with respect to alpha and then with respect to x. So, if I change the order of the parameters, this equals, I can write down 0 to infinity g of x, then I can bring it outside root over 2 by pi 0 to infinity f c of alpha into cos of alpha x d alpha into d x. Fine. Simply by changing the order of the integration, I can write down this. Now, please see this integral. This is the inverse Fourier transform of the function f x. That is, if I know the Fourier cosine transform of f x, then the f x equals, I can write down root over 2 by pi 0 to infinity Fourier cosine transform of f x into cos of alpha x d alpha. So, that this particular term can be replaced by f x only. So, this equals 0 to infinity g x into f x d x. This completes the proof of the first part, because the first part of the proof was 0 to infinity f x g x g s f x into g x d x equals 0 to infinity capital F c of alpha into capital G c of alpha d alpha, where capital F c of alpha is the Fourier cosine transform of f x and G c of alpha is Fourier cosine transform of g x. Now, once we have proved this, I hope that in the same fashion you can prove this one also of your own, that is 0 to infinity f x g x d x. Following the same argument, you can show that 0 to infinity f s capital F s alpha into capital G s alpha into d alpha. So, therefore, this you can prove it of your own using the same argument. So, this equals 0 to infinity f of c of alpha into f of g of c of alpha into d alpha, and which completes the proof of the theorem. So, please note that 0 to infinity f x g x d x equals 0 to infinity f s alpha into g s alpha d alpha equals 0 to infinity capital F c of alpha into g c of alpha d alpha. The proof of this part I am leaving it on you, because in the same fashion you can do it of your own. So, quickly let us see it. I am starting with the right hand side, 0 to infinity f c of alpha into g c of alpha d alpha. This is equal 0 to infinity f c of alpha into root over 2 by pi 0 to infinity g x into cos of alpha x d x. Without changing the properties, I can interchange the order of the parameters x and alpha. So, that this I can write down 0 to infinity g x into root over 2 by pi 0 to infinity f c alpha into cos of alpha x d alpha into d x. And if you closely look the integral within the bracket, third bracket, this is nothing but f x, because using the inversion formula, if I know the Fourier cosine transform of a function, then f x equals root over 2 by pi 0 to infinity f c alpha into cos of alpha x d alpha, which I am writing. Therefore, I am replacing that integral by f x. So, it becomes 0 to infinity f x g x d x, which completes the proof of the first part. And on the same fashion, I can prove that 0 to infinity f x g x d x equals 0 to infinity f of s alpha into g of s alpha into d alpha. Now, see, let us see the application of this. The first example is, I want to evaluate this integral 0 to infinity dx by x square plus a square into x square plus b square. So, please note this thing. These integrals are known integrals, and I have purposefully using this particular type of integral, so that you can understand that in general how much pain I have to take to evaluate one integral in the normal integration process. Whereas, if I use the Fourier transform or the properties of Fourier transform, how easily I can find out the values of different integrations. So, let us evaluate this integral. Please note, I want to find out the value of this thing. This is equals how much? Now, is it, you see, by observation again, the x square plus a square, this type of form is coming for the Fourier transform of the function e power minus a x or something like that. So, I am starting with, I am assuming that f x equals e power minus a x and your g x, this is equals e power minus b x. Why I am taking this? Because if you take Fourier cosine transform of this function, it will be a by a square plus alpha square, and which we will get one of the denominator, and for the function g x, if you take Fourier cosine transform, you will obtain the other denominator. So, Fourier cosine transform of e power minus a x equals, we know, root over 2 by pi into a by alpha square plus a square. So, this is your Fourier cosine transform function of alpha. So, capital F c of alpha. Similarly, Fourier cosine transform of e power minus b x, this also root over 2 by pi into b by alpha square plus b square, which you are writing as g c of alpha, the Fourier cosine transform of the second function. Now, you have this integral 0 to infinity f x g x dx. This is equals 0 to infinity f c of alpha into g c of alpha into d alpha. Already from the last theorem we have done this thing. So, from here, if you put f x and g x as this thing, you will obtain 0 to infinity e power minus a x into 0 to infinity e power minus b x dx equals 0 to infinity root over 2 by pi into a by alpha square plus a square into root over 2 by pi into b by alpha square plus b square into d alpha. Using this theorem, by evaluating the values, I can write down this thing. So, once I have written this, so 0 to this right hand side integral can be written as 2 by pi 0 to infinity a b will come alpha square plus a square, alpha square plus a square into alpha square plus b square into d alpha. This is nothing but 0 to infinity e power minus a plus b into x into dx, whose value, this integral value you can evaluate easily, which is e power minus a plus b into x by minus of a plus b, where x is ranging from limits of x is from 0 to infinity, and if I evaluate this integral, I will obtain 1 by a plus b. So, this value of the integral very easily I am obtaining. Now, replace alpha by x here. So, what we will obtain 0 to infinity dx by x square plus a square into x square plus b square. This is equals to pi, here pi by 2 will come on this side, pi by 2 a b will come downward. So, that on the denominator into a plus b is there. So, the value of the required integral 0 to infinity dx by x square plus a square into x square plus b square equals pi by 2 a b plus 2 a b into a plus b. Please note one thing, that what integral I had to evaluate to obtain the value of this, just I have to integrate e power minus a x form, nothing else. And using the earlier properties, Fourier transforms, and using the theorem which we have done, very easily we are obtaining the result of the given equation. So, if you see here, your f x and g x are this, you know Fourier cosine transform of e power minus a x, e power minus b x are this. So, that once I am obtaining this, I have this theorem, and f x g x is known to me, capital F c of alpha, capital G c of alpha is known to me. So, we are obtaining from that theorem 0 to infinity e power minus a x into e power minus b x dx equals this integral. So, that 2 by pi 0 to infinity a b by alpha square plus a square into alpha square plus b square d alpha equals 0 to infinity e power minus a plus b into x dx. If I evaluate the right hand side integral, I will obtain the value as 1 by a plus b easily. Now, replace alpha by x in the left hand side of the integral and you will obtain 0 to infinity dx by x square plus a square into x square plus b square equals pi by 2 a b into a plus b, where I am replacing alpha by x.